These are the distribution. Basically, like those 5 tasks are some VP optimizations. There are 2 tasks that are VP but doesn't require any of the optimization that we talked about yesterday, and the rest is not VP at all, but it's just taken from some test, right? And then, yeah, the RNG gives me better random distribution this time. Yeah, so these are the tasks yesterday. Yeah, actually, I intend problem I to be solved using divide and conquer, and I thought there's no convex hull or trick solution that worked, but so you guys managed to solve it using that. So yeah, you guys solved that using other than divide and conquer. For I, then the rest of the tasks don't have divide and conquer DB, because that's the only task that I prepared to be solved using divide and conquer. But yeah, again, many of you solved the problems with ways that are outside my intention. Like I didn't thought that solution exists. So yeah, you guys are great. But yeah, again, many solutions to the task. So yeah, yeah. Again, we'll try to, because I have some materials today, so we'll keep. Again, you can of course discuss, but we'll probably do some task discussions on Friday maybe, or yeah. Yeah, on Friday the materials are a bit short, so we probably have time to discuss some of the tasks and then of course continue on Saturday for the rest of the tasks. Okay, but before we talk about graphs, yesterday I mentioned that we cover some example tasks at the end, and there's one more task that I didn't manage to talk about, so we're going to talk about that first today, right? Okay, and yeah, so this task again, so let's set our mind back to divide and conquer and convex hull and the things from yesterday. So this task actually from IOI. It's 8 years ago, 9 years ago. Yeah, so the task is holiday, and this is not the actual. What I'm going to show you is not the actual formulation of the task, but it's like been reduced. So this is just one of the components needed to solve the actual task. The task is more complicated than this, but once you solve this, it should help you to solve the actual task. The actual task is it's not much more, but more complicated, and yeah, we won't talk about the other components of that task, but I'll discuss this component, this part, because it's related to our topic from yesterday. So let's say you're given a cities of n cities in a line, and each city has like a value, right? And then for you initially start at city 0. Okay, and then in each day, you can either move to a neighboring city, like if you are city I, then you can go to I minus 1 or I plus 1. Okay, but 0 does not walk to n minus 1. This is line, not a circle. Yeah, so, or in one day you can move or take the value of the city that you are currently in, right? So, yeah, and you can only take at most, in any city, you can only take the value at most once. You cannot spend several days to multiple times take the value of that city, right? So yeah, and then the question is for each number of days. So we try to solve 2n problems here, 2n queries, something like that. We want to determine the maximum total value you can get if you have d number of days. So yeah, how do we solve it? Oh, it can be 10 to the power 9. Any thoughts? Yep.
Just confirm, like, if I walk, like, for each day, like, I walk some sequence, then I get the key values for the most, like, I walk with some segments, okay? And let's say I have Z energy left. Then I must take the key greatest values from the segments, correct? Okay.
Yeah, that's the optimal solution. Yeah.
Okay.
Yeah. I mean, the problem doesn't require you to, but that's the optimal. That's the optimal solution. Yeah. Yep.
Maybe, I don't know if it's useful, but if you increase the number of days,
Okay.
the number of times you take the value will also increase.
The number of times you take, sorry?
Actually, you take the value, not move to the next city, but you take the value will also increase.
So you take value and then you move to the next city?
If you increase the number of days,
Uh-huh.
the number of times
Oh.
you take the value
Yeah,
will increase.
The answer will increase as well. Yeah, yeah, of course. But how is that helpful?
So maybe you can make merge there.
Sorry?
Divide and conquer.
Okay. How do you make it? Yeah, this time the distinct answer can be it's not small. It's can be n, I think, or even more. Maybe only n, but yeah. So the property, but yeah, it's correct. If you increase the z, the value will not decrease. Of course, yeah. But the possible answer, distinct answer, is not bounded by square root of n or anything now.
No, but if you have the b and the number of times you take the value,
Oh.
you can determine which values you will actually take. It will be
Okay.
the maximum from a prefix.
Okay.
And
So number of times means like the distinct, not the sum, but the distinct values that you take. Okay, yeah. And then?
so if you have a prefix
That's correct.
and you have the,
Uh-huh.
you know how many times you are going to take a value.
Okay.
You know how many times you are not going to take a value. So in which range are you going to look for the value, and you take the maximum in this range.
Okay, so you're saying that, and then you say you use divide and conquer. Right. You say you use divide and conquer?
Sure?
You use divide and conquer?
Yeah.
So what are you dividing the conquer with? The d, the value of d? Okay, so you say, let's start with the d, let's say n. And then for d equals n, you say you want to try the prefix like linearly. Okay, and then for each prefix, how do you compute the optimum? Because let's say you consider this 5, then you only can take n minus 4 because you need 4 days to walk here, and then you can only take the n minus 4 largest values here. How do you do that? But it's in the right direction, yeah. You don't actually need. You can use persistence.
You can use like the persistence of the key input values and still
Right. So yeah. You basically you can query like what's the sum of the largest key value from L to R. Using okay. So let's say we can answer this. So now we have the optimal starting point. Let's say this is the optimum prefix of and then what do you do?
And then we start exclusively for
Okay, for D equals n over 2 and D equals n over 2. And then for this one, you only look here, yeah? And then for this one, you only look here. Yeah, this is correct, actually. So, yeah. Yeah, the idea is we define for the value of D, and we know that, first of all, for a fixed single value of D, we can do a linear loop to try to find where is the optimum, where is the farthest city that we reach in the optimal solution, and then, this is now the structured problem to find the like, if you want to visit k cities, then you only have D minus k minus 1 days left, and you want to find what's the sum of the largest k minus 1 value to come to the structure problem. So it's possibly another of n. And then the observation is that if you increase the value of D, the optimal point becomes larger. Of course not becomes smaller, right? Because if D plus 1 optimal solution is here and D optimal solution is here, then actually for D plus 1 we can increase it here as well, something like that. But yeah, it's quite difficult. Why? So when we try to solve D equals n over 2, we only look until this point, and for D equals 3n over 2, we only look on the theta half, and we see a certain y is the total is n over. Okay. Any question? I think so, yeah. N looks correct. Okay. Okay, so that's one task that I left. Yeah, this is basically what I mentioned. This is one thing that I left from yesterday, so let's talk about today's tutorial now. Okay, so if you guys remember 2 days ago, I talked about today will be graphs, and I possibly cover graph connectivity stuff because I received a message from my social about it. But looking at yesterday's result, there is one task that requires you to find a bridge, and almost all of you solved it, so really we don't need to talk about it. But I just want to make one remark. I hope you guys probably have a library to find a bridge. I hope you know why it works, like what is DFS low, DFS now is used, especially for you like the IOI people, because you cannot use library, you have to write from scratch. So even though you have it, you have to know where it works, okay? So actually I have slides explaining about what DFS low function and everything, but let's just skip that because if any of you are not familiar with it or not sure why it works, come talk to me afterwards. But we're not going to spend 40 minutes or something explaining it. But maybe what we can do is, so I have all these slides to talk about DFS load, DFS load. Maybe we'll just skip it and talk about some problems. It's sad, yeah. Okay. So this is not the main thing today. I'll talk about the main thing is about funny graph properties. But yeah, let's just do this quickly. Some practice tasks about bridge and articulation point and SEC. But we'll just do this quickly. Yeah, I think some should be not that complicated. But let's just go through. Okay, so first, again, we are taking a look at IOI 2050 IOI problem. It's actually just a practice session. The problem is called graph. Cannot come up with better title. The title is just graph. So yeah, it's just like a standard articulation point, but now instead of finding a node that disconnects the graph, finding a node that only disconnects A and B. So given a node A and B, the question is how many vertices, or it can be modified to print out the list of vertices that if it's disconnected, disconnects A and B. Which, yeah, okay, so how do you solve it?
Make the graph adapt, sort of making that the edges go from another nearest to B to another larger from A for the beginning, and the same with the end, and you can count the number of bytes from A to each node and from B to each node, and in one node is the product if the growth of the path from A and the path from B is the same as the number of paths between A and B, that node is necessary.
This is a graph, not a tree.
No,
Yeah.
I mean a graph. You can make it a graph, solving the nodes, for example, by the distance from a node, from the node A, after from the node B.
Oh, okay, like a shortest path?
Yes.
Okay, so shortest path from A and then shortest path from B?
Yes, you can order you can put, orient the edges,
Okay,
and after that, if you have a directed acyclic graph,
okay,
you can calculate the number of paths from A to each node, DB, and the number of paths from B to B from each node, and in a node, the product of both things is equal to the number of paths from A to B, that node will be necessary.
so let's say this is the graph, and you say you run shortest path to give directions to these edges, right?
Yes.
So these edges will be here, but what about this edge because it has the same distance? Yeah.
You can find our articulation point,
Articulation point, okay.
remove them from the graph.
Okay.
Now do a DSU and find all the components without the articulation point.
How long does it take? Is it linear or is it what?
Yeah, like you use unit time to
Sorry, so you find the articulation point.
yeah.
Let's say there's a graph here and then there's a graph here. So this is the articulation point. And then you remove, so you remove all of this, and then
And if there's a path from A to B, this number is 0.
so every time you remove, you build a new DSU.
No, I first remove all of them, then I find
Oh, okay. And then?
if there's a path from A to B, there is no problem. There are 0 nodes.
Okay. But what if it's disconnected, UNG?
Otherwise, all articulation points will be in every path from A to B.
Find the articulation point,
Uh-huh.
and then you condemn every node that is like between one.
Okay.
You get a tree,
Yeah.
and you can find the path.
Basically what you say, right? Yeah.
All articulation points are
Okay. Yeah, I guess you can do that. Yeah, that should work actually. Yeah. Okay. Okay. Yeah, that works. That should work. Yeah. But another way you can do this is actually, this is why it's better if you understand all the DMS low and DMS none. Because what you can do is you don't need to find any articulation point at all. Just run your DMS tree with root A. Usually you can run DMS tree with any root, right? When you find articulation point. But in this instance, let's try it. Run root equals A. And then of course the only candidate file is the path from A to B in the DFS tree, right? Okay. And then node U is an answer is let's say P is the so let's say this is A, and then this is the DFS tree, right? And let's say this is B, okay? And of course there are some back edges, right? I hope you know DFS tree, back edges, DFS low, right? Okay. So only these two nodes can be the candidate answer. And let's say we want to check whether this node is the answer. Then let's say this is U, and find out which V is the ancestor of V that is the child of U. Okay, I just one more. Yeah, let's say this is V. Okay, so this is U and V. And if the DFS flow of V is going out of U, then this is not an answer. Otherwise, it's an answer. right? Because otherwise it means that anything from here cannot go out, cannot go up to the anchor store of view, right? Yeah. So this is very minor modification from finding articulation point. When you want to find articulation point, you have to make sure that all of this V, the DMS flow is outside of view, right? If there's at least one V that the DMS flow is not going up to view, then it gives articulation point. Right, that's how you find articulation point. I hope you know that's how you find articulation point, right? So now in this problem, instead of checking all of them, we just check the one that is closer to C. That's all. Right? Yeah. So you just modify the instead of taking this, instead of finding articulation point, you just check whether it actually disconnects P or not to A. Okay. Any question? Okay, if you're not familiar with DMS flow and DMS now, ask me afterwards during the break. Okay, more practice about this graph connectivity thing. This is from given a directed graph for each node, determine whether a cycle that is starting from that node.
Wait. What does the starting?
Like it starts from that node and ends at that node. There's a cycle, directed cycle that starts from that node and ends at that node.
That's not what an old nodes in the cycle.
Sorry?
What an old nodes in the cycle?
Yeah.
Tem como conversa não tá.
But there can be nodes that is not in part of any cycle, right? Yep.
Então a componente vai conectar dele nesse número.
Yep. Yeah. It's quite simple. So yeah, just that. Yeah. But you have to check whether the strongly connected component has more than one element or not. If not, if it is, that means it can go out, and by definition of strongly connected component, it can go back again. So there's a cycle, right? Yeah. So yeah, that's so it's simple. Just check whether each node is alone in the strongly connected component. One more. Actually, there's two more. Given directed graph, determine whether which nodes can go to all other nodes. Okay.
Check if it's from that supernode.
But we want to find, we want to check for all nodes. So that will be answer, right?
Yeah.
So the only candidate that is possible to go to all nodes is the strongly connected component with biggest T. I don't know how you say that in English, like the DFS out time.
What's that?
Like the time that you go out of the DFS. I don't know the name of it in English.
How do you DFS? What's the order of the DFS?
No, like you do like Kosaragi to find strongly connected components, and the last strongly connected component that you do. This is the only component that is a candidate for being for reaching all.
So you run DFS only from that node.
Yeah.
And
so
then
you choose any node from that strongly connected component and see if you can reach all nodes.
Okay. Yeah. Okay. And then if it is, then all nodes in that strongly connected component is the answer, right? Yeah. Okay. Okay. So if A and B is in one strongly connected component, then the set of reachable vertices from these two nodes are actually the same. Okay. So you run a strongly connected component. Yeah, you can do what it says, or you can group. Basically create like an SCC graph where you group each node in the same SCC together, and then at the edges if there's like a node from this SCC to this SCC, right? And then there's another solution actually. You can choose a candidate node that has no in degree, right? Because if there's an in degree, there's no way that node is an answer, because you cannot go to the like, if there's an in degree here, this node cannot be the answer, because this certainly would be able to go here. Otherwise these two will be in one SCC, right? So you can choose the candidate, you can choose a node without an in degree. And then run and then check if it visits everything, and then if it is, then this is answer. If there is two nodes without any in degree, then there's no solution there. Obviously there's no solution. Okay, yep. Cool. Last. This is from 10 years ago, ICPC Jakarta Regional. Given a graph, find the number of pair of nodes with unique path.
Caminho único, você tem que ver, tipo... Ah, ok, achei.
Sorry?
The fast way only bridges.
Paths on what?
Fast way bridges.
Yeah. Sure, yeah.
So, you make a graph of only bridges in the original graph.
Okay.
And the number of unique paths is the number of paths in this graph. Because if you pass through a non-bridge to reach a node, it means that there's at least two disjoint paths that can go in like a component.
So it becomes like just finding how many components and then choose
Yeah.
two and then plus. Yeah, okay.
Yes.
Okay, yeah. Simple enough, right? Yeah. So from the original graph, destroy any edge that is not a bridge. Yeah, so the other, like usually we destroy the bridge and then make the rest one component, but this is now the other way around. We take out the rest of the edges that is not bridge. Right, okay. Yep. Okay. Any questions? Okay. So now let's go to the real graph thing.
Mano, tinha aquele problema lá do ponto, acho que era M-10.
Okay, so graph and properties. So yeah, today is going to be a bit how do I say? So it's not it won't be like generic techniques that you can use to solve many problems, but it's more like several properties about wave graph that you might not have known before, and it might help you to solve only like few number of problems, but yeah, it's good to know anyway, right? Okay, so yeah, more like I just need just like like yeah, fun to know stuff. Okay, so first of all, prerequisite, as usual, you know what's graph. Of course, we just talked about it anyway. I hope you know max flow. I hope we don't need to talk about what's max flow in this class and how do you find it. Okay. Okay, and this is something that you might or might have not known. Do you know what's proof by induction? Oh, okay, good. Okay, so yeah, let's talk about, first of all, let's talk about planar graph. So yeah, probably you have known as well. It's a graph that can be drawn. So the key here is can be drawn. Even though they are drawn with crossing edge, if it can be adjusted so that it doesn't cross, it's still called planar graph. So this is also called planar graph, right? Okay, and yeah, and there are many cool properties that might help you to solve if the graph is guaranteed to be planar. First of all, is there's this identity, right? Again, some of you probably know, but you can be expert without knowing this. So yeah, so maybe some of you still don't know, but yeah. And the proof is induction. Maybe I can go just quickly. Basically, if there is just one node, it's obvious. It's true because P is 1, number of phases is 1, and H is 0. Okay, and M is the number of phases. Like let's say there's a planar graph. And the number of phases is P. The outside phase is counted as well. Okay. Like yeah. Okay. And then yeah, by induction we can start from this, and any graph can be built by adding nodes or edges, right? And every time you add a node, sorry, this has to be connected. The graph has to be connected. Okay. So every time you add a node, you have to add edge as well, and both of these sides will increase. And if you create, if you add an edge without creating a new node, you will increase one phase, right? So for example, if you add this edge, you will increase the number of phases as well. So both this and this will increase. Right, so yeah, this is true because you can start from here, and then you can, and then every time you add a new node or a new edges, this will remain true. So you can, for any planar graph, even if it's very big, it's true by induction, right? Okay, and then the probability of this identity is that the number of edges is actually bounded by E minus 6, and the reason of this is because I don't actually remember how to do it. Something like each face can have three edges. So the number of face is wait. So E is P plus F minus 2. And then face is bounded by something because the number of so each face can be in edges. So the number of face is bounded by 3F divided by something like that. I hope it's correct. Yeah, because to make a face, you need at least 3 edges. And each edge can be shared by 2 faces, right? Yeah. So the number of faces is bounded by this because you need 3 edges to build a face, right? So yeah, if you plug it in here, you get this. Sorry? Yeah, sorry, the other way around. Yeah. So if you have E edges, then yeah, the maximum number of faces is 2E because it can be shared by 2 faces, but you need divided by 2. Yeah, correct. Thanks for correcting. Yeah. And then if you plug it in here, you get that. Right. So yeah, I think you can figure out how this works. Just solve yourself. Okay. So yeah, basically the number of edges is linear to the number of vertices, right? So let's say you're given a problem that usually requires P times E solution. Like let's say you're given an awaited graph for an open surface path, right? So usually you need to do OE and then start from all vertices becomes P times E. Right? The graph is standard because the number of E is P becomes P squared. Okay? Yeah. So that's why it might be beneficial, right? Okay, this is the interesting one. Try to prove this. Let's say there are n points on a 2D space, and the distance between a pair of points is guaranteed to be at least 1 centimeter, or 1 unit, or whatever, right? And then we want to prove that there's at most 3n pair of points that have the distance exactly 1 centimeter. How do you do this? Yep.
If you connect 2 points that have distance exactly 1 centimeter, is that graph doubling? You have 2 lines of 1 centimeter, and they cross one of the 4 edges that would be less.
Yep, exactly. So yeah, so if you connect, like let's make it a graph. Each point is a node, and if you connect 2 points with a distance exactly 1 centimeter with an F, then the graph is planar, right? Because yeah, as you mentioned, if there is a crossing, then any of this distance is less than 1 centimeter, which is a contradiction. Assuming that, because just now the assumption is all nodes are at least 1 centimeter. Yeah. If there is a crossing, yeah, some of these for distance it cannot be at least 1 centimeter. So the graph is planar. If you do this graph, and you know that the number of edges in a planar graph is not more than 3m. Right? Okay. Okay. Now, because the number of edges is bounded, we know that there is a bounded by that number. We know that in a planar graph, there is a node with degree less than or equal to 5, right? And this is by contradiction. Right, so yeah, I think it should be easy. So basically, you assume that there are all of the degree has 6, all of the nodes has 6 degree. The number of edges will be 6 times p divided by 2, which is 3p, and cannot be, right? It should be less than 3p. It should be strictly less than 3p. Okay? The number of edges, right? So yeah. So basically, and having the graph with this property, like there is a node that satisfies something, usually helps for like induction-based proof, as we'll see later actually. So yeah, basically, there is, you know about coloring graph, right? So we want to color with fewest colors as possible, so that each neighboring vertices have different colors, right? And because there is this property just now, we can do 6 colors in an easy way, right? How do you do this?
Assign one and then assign the other 5.
No. How do you assign one and then assign?
Oh, sorry.
Yeah, because the theory is that we know that there is a node that has 5 degrees, but not all of them. Some nodes may have a lot of degrees.
I think you choose a node with degree 5 or lower and put an arbitrary color in it.
Put what?
Color it in an arbitrary color.
Okay.
Then take it out of the graph.
Okay.
The graph that you have now is planar, so there have to be another node with degree 5
Yes.
or lower.
Yes.
Repeat until you reach.
No, but when you say you color the node arbitrarily and then you remove, then it has several neighbors, but the neighbors must know its color, right? So the problem now becomes dependent on the node that you remove.
You do this algorithm, but instead of coloring the node with degree 5 first,
Okay.
you color it last.
Okay.
So you'll remove them in this order,
Yes.
and you color in the opposite order.
Okay. And then.
So what you will have is that every time you color a node, there is at most 5 colored nodes
Yes.
that were colored.
Okay. Yes. So yeah, basically, yeah, close, but actually the opposite way. We color the rest of the graph first instead of coloring the node arbitrarily. We color the rest first, and then yeah, as you mentioned, yeah, we need to make sure whenever we do induction like this, when we remove the node, the rest of the graph is still planar. Of course, like removing nodes and edges doesn't make it more complicated, right? So it's still planar. There's still a node with less than or equal to 5 degrees, so we can recursively do that. And then when we already have the rest of the graph colored, then this node, because there's only at most 5 degrees, the node that we take out initially, there's only at most 5 degrees, we still have one color, at least we still have one color remaining, then use that color. So yeah, that's how you do this kind of induction-based construction, right? Okay? Okay. Actually, there's a way to color it with 5 colors, and this is more interesting. Of course, you know there's a 4 colors, but we'll go slowly. So the 5 is still feasible to discuss. Do you know how? There's probably in wiki, but do you know how? It's quite interesting actually, the construction of this.
I have a general idea, but maybe not exactly.
Okay.
So you do like the same idea of removing the one that has the low degree.
Uh-huh.
But when you add it back, you try to rename the colors so that you get like no conflict. And that should always be possible.
No, but so let's say we take out a node with 5 degrees, right? So the worst case is if when we color the rest of the graph, all of these 5 colors are distinct. If it has only 4 distinct colors, we're fine. We can use the 5th color, right? But if all of these are different, what do? You rename? Sorry, what do you mean?
Yeah, I want to like recolor some of them. Okay, so maybe just think a bit about some more. But I think you should always be able to like recolor them and some of the, like some paths or something.
Yeah,
like
but like if you let's say you change this A to B, something like that.
Yeah.
Yeah. But let's say this A is connected to B, so you have to change this as well.
Yeah.
And then if you flip them, you can at the end flip this, and then this becomes B, this becomes A. This was right. So yeah, it's not as simple as that. Sorry, iteration.
You can do that. You can find many different combinations because of the proportionality. They can help swap, and like that you can make an argument that there's some possibility that always works.
Yeah, basically that. Yeah. So yes, actually fine. So for 5 colors, only only this property is not enough. Just now we see for 6 color theorem, if the graph satisfies this corollary, it's enough. We don't need the planarity anymore, right? As long as there's a degree with degree, as long as there's a node with degree at most 5, we can color it with 6 colors. That's fine. But now for 5 colors, we still need the planarity property. So basically, the idea is what you mentioned. We try to recolor, but so basically, you try to find a path from A to C that has alternating nodes between AC, something like that, right? So you find this path. Okay. If there is no path like this, then you can swap this A to C, and then it's fine. Right? So you can swap this A to C and then do like if there's a C here, then you also switch this to A, right? Then that's just fine. The problem here is that if there's a path that connects A to C, something like this, right? If there's a path that looks something like this, then if you toggle this C, A, then it will become A. Then it's useless, right? So the problem is only if you have something like this, right? But if you have something like this, then it means there cannot be a path from B to B that is alternating BD, right? Because it's planar. Right? So that's why you do this. You choose two nodes that are not neighbors, let's say in the order. If there is no path that looks like this, then you can easily do it. But if there is, then you choose another pair of nodes. And because you find out this, there will be no path that is alternating with BD. Okay, and then of course some of you might have known that the four color theorem on parallelogram as well, but if you discuss the proof now, we'll begin on the next one. Sorry?
It wasn't clear to me how you do the construction.
Okay, sorry. Yeah, so basically let's choose this A, and then let's toggle it with a node that is not its neighbor.
Okay.
Because it's planar, we can some kind of like sort this in a clockwise order or something, right? Okay. So let's say we choose A and C. So for A, we change it to C. Okay. And then of course because it might have a neighbor that is C. If it's C, we change it to A, something like that.
Oh, okay.
But the problem here is that if there is a path from A to C that is alternating between A and C, right? This will be a problem because if we change this to C, AC, this will become A.
Okay.
Right? But if that's the case, then that means there won't be a path from B to B that is also alternating between B and B.
Oh, okay, that's smart. Okay.
Yeah.
Okay. That makes a lot of sense. Okay.
Yes. Yeah, so basically, if there's no path here, we change this to C, and with DFF, there's actually a C, we change to A, and then if this A actually connects to A, we change it back to C, and if there's no path connecting A to C with alternating like that, then we can safely change this to C, and then this becomes A. Right? Yeah. I haven't tried to code it yet, but by brute force it seems like you can do everything MM, but maybe you can optimize it, but I haven't tried to code it. Yeah. And of course you have to try to find the order of this clockwise, which becomes complicated, but at least you know that you can color it with 5 colors. Actually you can color it with 4, but this is the proof that you can color it with 4. Okay, and then fourth color theorem is very complicated proof that just found out in the last 20 years or something. It's a very complicated stuff. And I think even until now, the proof is assisted by a computer, like a brute force program that is able to prove it. So if you can somehow prove it without computer assisted, without any kind of brute force, then it will be kind of new proof that you'll probably be famous. So just to know, You can always color planar graph in 4 colors or less. But if there is a problem that asks you to actually color them, then just give up because the proof is not constructive. Right? The proof is very complicated. It's not construction-based proof. So it's still a very hard problem to actually color them. Like given any graph, color them with 4 colors is still difficult.
What's the best bound known
Four.
for no,
Four.
what is the best algorithm? What's the time bound? The best algorithm known?
Oh, I don't know actually. Oh, yeah, I haven't checked, but yeah, good question actually. Yeah, for 5 color maybe, because 4 color is just too hard. Of course, you can do it 4 to the power of n, but it's just stupid. But yeah, 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 I don't know actually for the actual time complexity. We want to what's the best known yet? I'll look that up. Yeah, and this 4 is actually like in terms of the number of colors, this is the lower bound. Like there is of course like if there's a K4 like a complete graph of 4 nodes, and this is planar, right? Of course you need at least 3 colors to color this. At least 4 colors to color this, right? So any graph that has this as a subgraph, you need 4 colors. So this is tight. You cannot bring it down anymore. Right? Okay. Yeah, and then because of the 4 color theorem, we can solve a maximum click problem on a planar graph, which is otherwise a hard problem to find a maximum click. Maximum click is a problem, in case you don't know, it's a problem to find a subgraph that is complete, right? So you choose a set of vertices, and each of the pair of vertices have to have an edge. That's a maximum click problem, right? Okay, so how do you solve maximum click on planar graph?
It's a maximum click because it's 5, you can color with 4.
Okay, so basically, so if there is 5, if there is a click of size 5, you cannot color it with 4 colors, right? Which contradicts the 4 color theorem. So, basically, if there's a click size X, you will need X colors only to color the click itself, right? So you need at least X color to color the graph. Yeah, so the problem now becomes just check whether there's a click of size 4. If there's not, you should check whether there's a click of size 3 and so on, right? So how fast can you do this? Let's say the constraint is this. How do you find a click of size 4 in this constraint?
So perhaps you can take a node that has a low degree,
Okay.
and you try to find its 4th place.
Okay.
If it's not, it's just not in any 4th place, so you just remove it. And I think that might be quadratic, maybe.
Oh, that's interesting. I never thought of this solution before.
Because you have 25 ways to combine your neighbors, and then you search for another extra node, and that should be easy, I think.
It's linear, yeah.
Is it linear?
It's linear. Okay. Okay. Well, I originally thought it's quadratic. Okay, so that's why the constraint is smaller. Okay, does that work though? Yeah, it should. It sounds good.
Wait, why was here here?
So you just take some node with a low degree, and if it's in a 4th click, 2 of his neighbors, all 3 of his neighbors have to be in this click, of course.
Yeah.
So you just write all the combinations of 5 things.
Yeah.
That's
Okay.
linear.
Mm-hmm.
There you
So that becomes like 5 cubed times n, something like that, right?
Yeah.
Okay, yeah, that works. Okay, sure. Again, we take advantage of the property that there's a node that with at most 5 degree. I forgot to take advantage of that. So my solution is quadratic, but we can do that. Okay, thanks. Okay, any question? Okay. So next is bipartite graph, but let's just go fast here because I think you know what it is. It can be partitioned L and R so that all edges connect on the L and R. Warming up, if you just want to find the partition, easy, just do GFS and blah 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 blah. Yeah, I know you know it. Okay, and then maximum bipartite matching. Of course, you can do max flow, but it's complicated, too long to code. There's an iterating path algorithm. where basically if you go on the R, you know what's the match of the L, you just, instead of do BFS from there, you just go to the left using the H dash match, blah blah blah, and then, okay, this is something that you might not have not known.
Sorry.
So the alternating path algorithm is O times OP times E, because for each vertex you might need to traverse all the edges. Some of you might have known Hopcroft card, which takes E times square root of V, I think. But if you do the alternating path algorithm and you start with randomized path, like greedily, like basically like do a greedy where for each node you find any node that is not matched yet, take any, like let's say this one. And then for the next one, let's say this one. And then if for this node, all of the neighbors are already visited, then you just skip it, right? And then do that randomized way, right? We just take any, right? And then after doing that, we do it one more time, except that if a node is not matched yet, we do the alternating path algorithm. We call the match method here, right? And that actually becomes fast. I think it's even like expected OE plus E or something, I forgot, but or maybe something like OEV. So yeah, instead of putting Hopcroft card, if you're feeling lucky, you can put this. And it's not just feeling lucky, it's generally fast. It's very hard to make it OE times E. I don't actually know why, but yeah.
Wait, so what do you actually randomize?
For each node, if there is several choices, you randomize.
Oh yeah, okay, so you randomize the adjacency leaves. Right?
Yeah.
Okay. Yeah, okay.
Yeah. Okay, but yeah. And of course, if there is a weight, you have to use Minkow's Marx law or Hungarian algorithm. I hope these words make sense to you. I hope you know it. If not, ask me later. Yeah. So, okay. So let's take a look at some bipartite matching application, bipartite graph application. So yeah, let's say actually this is not bipartite, but yeah. So let's say you are given a graph in the form of two complete disconnected subgraphs, like 2 clicks. Find the maximum click. Easy, just take the maximum, right? Between the two, right? But now let's say the graph is 2 clicks, but there can be edges. So it's something like, let's say, like this, and then there's a complete 5, and there can be edges in between. Okay, and this might actually form a bigger click. That yeah, this can actually be this 6 nodes is actually a bigger click, right? Yeah. How do you find the maximum click? So yeah, the problem is like, let's say you're given A and B, and then yeah, and then you're given a list of extra edges here, and then how do you find the click? Right. How do you find the maximum click?
If you expand the click, like on the A side, if we can expand the B click, we have to have edges to all the nodes.
Yeah, but how do you find the maximum? Like, how do you find like which subset of B that you can put into A, like using that?
No. They just like do a bunch of DFS or something like that. I don't know. So like you just need to check the edges, right? Just check that it has all the edges.
Oh, sorry. The answer might be partially, like might be this one as well.
Ah, right.
Yeah, if there's no this edge, then yeah, might be partially as well. Yeah.
What if you greedily take the node with the biggest degree? Because if you let's say the clicks are like a click of size A and a click of size B.
Mm-hmm.
If there's a node with degree bigger than A and B, then it's part of both clicks, right? So what I'm thinking is like take all the nodes with the biggest degree and like maintain the new degrees of all the other nodes, and like
You're
spray
saying the
that
no,
works.
the maximum degree must be in the part of the answer.
Yeah.
I think that might not be true. Wait. Yeah, because you can do something like, let's say there is a click of size 3 here, and then there is a click of size 4 there. Wait. Yeah, it's something like this. If this, let's say there's a click of size 7 here and there's a click of size 7 here. I won't draw the clicks, but yeah. The answer can be something like this, no? No, but this will have many edges.
If the down one connects to everybody on the left side and the string is circulated also connects with everybody, the lowest one will have the most degree, but it won't be part of the click.
No, but if it has the highest degree, then it's part of both clicks. Like it can either be part of one click or the other click of both clicks. So it's either part of the high or of the max click, or it's part of both clicks. Like if you,
I think I have the solution.
Okay. Let's talk about that solution first.
but like if you take the node of highest degree, it's either part of the max click or it's part of both clicks.
What two clicks?
The graph is made of 2 clicks.
You cannot be part of both, right?
Yeah, you cannot be part of both. The 2 clicks here are disjoint. So there are 2 disjoint clicks, and then in between these clicks there is additional edges.
Oh, okay, I understood the problem wrong then.
Sorry.
I thought like there was a set of nodes that were from one click and a set of nodes that were from the other click, and they may be.
No. They
Okay,
are not. They are not shared edges.
Okay.
Shared partitions. Yeah.
Okay.
Sorry. Yes.
I think I have a solution.
Yes.
You take the complement of the graph,
Okay.
and then you have a bipartite graph,
Yes.
and now the biggest click turns to be the maximum independent set. And because you have a bipartite graph, you can do it with axiomatic.
Yes. That's the solution. Yes. So yeah, I purposely make the graph weird so that if you complement means that if an edge is missing, then it becomes an edge. Basically, flip the edge. Like if it's missing, then there's an edge. If it's not, then if there is, then it's missing. Yeah. If this kind of two clicks becomes now, there won't be any edge because the complement of the click becomes no edges at all, and then this becomes a bipartite graph where the edge is the complement. If previously there's an edge here, we don't have an edge here anymore. Yeah. And then yeah, why is this a maximum independent set now? So yeah, basically you can see that if we choose a set of nodes, let's say this is the set of nodes that we choose, you can see that if they are not adjacent in this graph, which is the required condition for the maximum independent set, then in the other graph, in the complement graph, they are actually adjacent. So yeah, whatever set you choose here as independent set is a click in the original graph, and vice versa as well. So that's why this problem is equivalent, and that becomes optimal. Yeah. Yeah, and yeah, you probably have known this already because you already can answer. So yeah, there's this Conics theorem. For those of you who are not familiar, yeah, you can read the proof in yourself, or even if you know about this but don't know the proof. It's a bit hard, but still feasible if you want. And actually, you might have to learn about it if you want, because sometimes the task asks you to construct what's the minimum vertex cover. So you know how to find a matching. But from this matching, you have to figure out what's the minimum vertex cover. So you have to know the proof, and the proof is by construction. So if you know the code, you can actually construct the minimum vertex cover, right? I won't talk about it. Hopefully you can learn yourself. Or if you have questions, you can ask me. And oh yeah, minimum vertex cover is a problem where we want to choose as fewest vertex as possible. But each edge has to be covered by at least one of its endpoints, right? So we want to mark like as fewest points as possible so that each edge, one of its endpoint is marked, or both of its endpoint is marked. Yeah. Of course, we can mark all the nodes. That's okay, but we want to minimize the number of nodes, right? And yeah, and no, just now we don't want minimum vertex cover, but we want the maximum independent set. That's just the V minus. So basically, maximum independent set is another problem where you have to choose as many nodes as possible, but now for each edge, only at most one of its endpoint is chosen, right? And this problem is actually again equivalent in the sense that if you have several nodes, and this, let's say this node is the vertex cover, then the rest of the nodes, like this is true not for bipartite graph or planar graph. This is for any graph, right? If this set of nodes is vertex cover, then we know that there is no edge connecting the vertex not in this set, right? So that means this set, this red set is actually an independent set, right? And if this black nodes are minimum vertex cover, then we know the other nodes are maximum, right? It's like a dual kind of thing, right? Not duality, but yeah, no, you get the idea, right? So yeah, so yeah, this and yeah, because of Konig's theorem, you can also find a maximum independent set in a bipartite graph, right? Which is just simply the number of vertices minus the number of bipartite maximum bipartite matches. Right? Yeah, that's just what I mentioned. And then yeah, again, maximum click is a number of edges. Yeah, yeah. Fish vertex cover. The rest of the vertex is actually a click in the complement graph. Okay. Yeah, actually. Intended to go through this slide first before going back to this problem, but yeah, we already solved it. So yeah, and then the graph is the complement is bipartite, and then we want to find minimum vertex cover in the complement graph. Yeah, okay, blah 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 blah. Yeah. Okay, now let's talk about minimum path cover. Again, some of you have probably known this, but yeah, let's say we have a directed graph, and we want to find the minimum number of paths to cover all vertices. And let's say the paths can be overlapping. So let's say if there is this graph, yeah, you can do this and you can do this. So it's only two paths required, right?
Okay.
So how do you solve this?
I saw this problem before today.
Sorry?
I saw this problem before today.
Okay.
Okay. So what you do is for every node you wait. Okay. Wait. So mas só que tipo você.
This is directed graph, directed graph. This is important that it's directed. I need to.
Não, mas tipo.
Yeah.
You create the I forgot the name, but if there is a path from A to B, you create a edge from A to B, and then you get the matching of this. And then you create every node on the left side of a bipartite graph and every node on the right side of the bipartite graph. And if there is a path from A to B, you create a node, an edge A to B, and you get the maximum matching of the maximum.
By path, you mean an edge, right? If there's edge from A to B, you add A to B. Not a path. Or there is a path.
Path.
A path?
Path.
But
yes.
we allow duplication here. Okay.
Oh, I think it's like n minus the side of the greatest matching.
Okay, your solution is not correct. There's a text. So. Oh wait, no, you're correct. Sorry. Sorry, you're correct. Yeah. So if if there's a path from A to B, you add, right? But what if there is a cycle? Let me think.
Direcionado, sim, é um DAG. Não, porque os caras não são disjuntos. Porque, tipo, você pode ter vários caminhos entrando e saindo com o cara. Qual que é a modelagem? Porque pra ser é foda essa porra, velho. Assim vai sair entrando.
I think that works at high complexity than just having the edge. Because you have to compute if there is a path from each pair of nodes.
Tá, como é que é isso?
Vai ter um caminho em cada vértice. Ah, você não precisa passar por todos os caminhos?
Okay, let's figure out why his solution does not work. Yeah, because this should not work.
Wait, the paths need to be disjoint?
So each path should not visit a node that is already visited, but different paths can visit a node that is already.
Não, mas então. Não, então isso aí seria tipo.
So yeah, if the graph is like this, then the answer should not be 1, and I think his solution is 1.
Não, deixa porra. Não tá
Like
certo,
the optimal
porra.
path never jumps from a vertex to a vertex like that you can go not directly. And that's why that solution works, I think, but high complexity.
But his solution might visit a node more than once like this. Like this, for this case, the answer should be 2, but his solution is 1. Yes.
If you don't allow visiting the three nodes at five, why doesn't it?
Yes. That's what it's going to be on the next slide. But yeah, so yeah, basically, this doesn't work. The solution, the bipartite matching does not work because of like if there's a cycle, your solution might visit a node more than once.
In this solution, you do a matching, right? And so each node has n degree at most 1, or did I misunderstand this?
So in this graph, his solution will be something like, let's say 1, 2, 3, 4, 5, and then you will get a matching that looks something like
Oh, this graph is not
this,
perfect.
right? And then you C minus the number of matching, right? So you get 1.
I am pretty sure there is a theorem about this on the CSS book. And
but there is something missing in this slide that makes this does not work. Yeah.
Wait, I'm confused. Like, how does the solution work? There's a node here. There are 3 nodes going from here to the center node, and 3 edges going out to 3 other nodes here. Because like the matching would say that you can pair at most this edge, this edge, and this edge.
You create if there is a path, so you create this tree to this tree too.
You create a directed edge from this to this.
Yes. It's not just the edge, it has to have a path. Any path.
Yeah, okay. Let me clear up the confusion here. Yes, sorry, you want to say something?
Yes, so I have an idea.
Okay.
The paths can like overlap and cycle.
Different paths can overlap, but one path cannot visit the same node twice.
Okay.
Yeah.
Never mind. So the graph can contain cycles.
Não, mas os
Let's say yes.
os
Yes.
caminhos não.
Because I didn't write anything here that says cannot cycle, right?
Várias vezes. Mas
I don't know
vários
what's the
caminhos podem
difference
usar o
between
mesmo
this
vértice.
problem and the problem on this.
Yeah, so this problem is actually impossible to solve, as you mentioned, because Hamiltonian part problem, right? So if you know Hamiltonian part problem, it's a question whether you can visit all the, you have a path that visited all the nodes, right? So if you can solve this problem, then you can know whether the answer is 1 or not. And if it's 1, then that means there's a Hamiltonian part, right? Right? So this problem is actually like harder than Hamiltonian part problem. Because using this problem, you can figure out whether there's a Hamiltonian part or not. Right? And Hamiltonian part is a hard problem. I'll talk about it later as well, why it's hard and so on, right? But yeah, for now just take it that Hamiltonian part is hard and we shouldn't be able to solve an even harder problem than a Hamiltonian part problem, right? So as you mentioned. So yeah, the key part that is missing is your solution only works on a DAG. Sorry?
I didn't understand why this is.
On DAG? Oh, okay, yeah. We'll talk about it, actually, yeah. But first of all, Hamiltonian part on DAG is polynomial. How do you solve it? Sorry?
O mesmo caminho não pode passar
Okay.
pelo menos verso duas vezes. Dá o caderno. Dá o caderno.
By maximum paths, you mean number of paths or number of visitable nodes? Oh yeah, okay, yeah. Yeah, okay. Simple, right? If there's no, if it's DAG, you can do DP. So now this is solvable, and that problem, even though it's harder, it turns out to be solvable as well. And the solution is, yeah, what you mentioned. Yeah, so, and we'll talk about why it works. So basically, we create a bipartite graph, and then, yeah, so there is two versions here. First, let's say the paths, the paths cannot visit the same node twice, like just now when I illustrate with this example. Okay? Let's say, for now, let's say the answer is 3, because once you do this part, you cannot do this part. Okay, so each node can only be visited with only one path. Okay? Right, and you cannot do less than 3 paths if one node can only be visited with one path, right? If that's the case, then the solution is this. For each edge ij in the original graph, we add an edge from the left of I to the right of j, similar to what you mentioned, but slight difference. And the minimum path cover is the number of vertices minus the maximum bipartite matching. You want to explain why? Do you know why this works?
I think you can like create a path between the matching, and when there is no matching, you can create the path. So you like have to add one. It has like its n minus.
Yep, exactly, yeah. So, so the representation of the matching is that if Li is matched to Rj, then I and j is used in one of the paths, right? So in this case, let's say there is no this, so it's DAG. And let's say this is the matching. Okay, then yeah, this matching represents to this path, this and this. Right? Okay. So yeah, and we know that every time there is a node that is not matched, yeah, like this 4 and 5 here on the left, this means that this is the end of a path. Right? And the number of paths is just simply how many ends of a path are there. So P minus the number of matching, right? And of course, yeah, to give you another example, let's say the path is actually, we do this, we get a matching that looks something like this. Yeah. Okay, so yeah, there's actually like one-to-one correspondence between matchings and paths, and that's why if this is maximum, this is maximum, because otherwise if there's more here, then there will be more here as well, and yeah, you get it, right? Right, so this is why it works. Yeah. And then, yeah, actually, exactly what the problem, what was before. Let's say the paths have, it's not necessarily disjoint. So in this case, you can create a path that looks like this, and the answer is 2. Now, you cannot do this anymore, because now, yeah, this will only go to like the matching will only match with either this or this. You cannot match twice. So, so yeah, let's say, yeah, you get the idea, right? So if this is the bipartite matching, you only get 2 matching, either this and this and this to this, or this and this and this and this, or this and this and this and this. But the maximum matching will only be 2. Right? Because this node cannot be matched twice. Right? So now if the graph, if the paths not necessarily disjoint, you do what, you say, we actually compute the transitive closure. It means that we convert the graph such that if there's a path from U to V and V to W, we also add an edge from U to W. Because in this patient now, we can interpret this as the path can like jump. Right? Because it can skip nodes. It can skip nodes that have been already visited before in the other path. So now we treat it as the path can jump over several vertices, can skip several vertices. Right. So we compute the transitive closure of the graph by using you run DFS from every node, let's say, and then do the matching. Right. Any questions?
What would the matches mean with that matching? Like in the previous one with that, if we match an edge, then that edge was for that.
Right.
In this case, like for that graph, what would be the matching exactly?
Actually, same thing, but the matching will be, so let's say this, right? The matching will be something like 1, 2, 2, 3, and 4, 5. But now, when you want to actually recover the path, this edge might not be there. So you have to actually run a DFS to find the actual path from 4 to 5. Yeah.
Ele tinha mostrado esse sim, era não disjoint o problema. Aí ele passou para a função do disjoint agora.
Não, cara, você tá muito doido, galera.
Todo mundo tá falando função para não disjoint.
Era disjoint.
Any questions? Okay. Okay, next let's talk about perfect matching. Basically if the size of in a bubble type graph, if the size of both group is the same, then if the number of matching is n, that's perfect matching, it's a full matching or whatever you want to call it, right? And there's actually a theorem called Hall's theorem. If for each subset of vertices that from L, or you can do it also from R, it's the same thing. But if for every subset of L, the number of nodes that the number of right nodes that you can reach from these nodes are bigger than X, the subset size, then basically let's read the notation first. For each X of subset, say Nx is the number of edges. So let's say, so if this is X, then this is Nx, right? If this is X, then Nx is empty set, right? Okay, so that's this is full. Okay, so let's say there is an X, and for each subset of L, if Nx, the size of Nx is at least X, the size of X, then there is a perfect matching. Okay, this direction is obvious, right? So if there is a perfect matching, of course the condition is also true, right? Because otherwise, if there is an X where the size of Nx is less than size of X, then you cannot match these two nodes, right? Because there's not enough nodes to pair this with, right? But what's more interesting is that the other direction is also true. So if all of the subset satisfies this condition, then there's actually a perfect matching. So the proof is actually quite cool, and we do it by induction. If the size of the bipartite graph is just one node on the left side, it's obvious, right? And if there is an edge, then it's a perfect matching. Otherwise, there's no perfect matching. Obvious, right? So for L equals 1, the theorem is obvious. But then the induction is that basically we assume that it works for everything less than m. and we try to prove that it works for M, the size of L. Dari means off. Forgot to translate. Okay, basically, the proof of why this works is that, yeah, we do it by induction. So, let's say we want to prove why it works for L, size of L equals to 4, okay, and we already know that it's true for size of L smaller than 4, right? Then we first check whether each proper subset of S, proper subset means is the subset but not containing everything, right? That's what it means of proper subset. Let's say for each proper subset the size of NS is greater than S, right? In this case, you can actually take any edge estimating, like let's say this edge, right? And the rest, these 3 nodes, and these 3 nodes, will actually satisfy the induction case that any subset of this, the n is at least x, right? So, yeah, that's fine, but let's say there is a proper subset of S where NS is S, then we can divide the L into two sets, where each of them satisfies the induction case, and we can solve the problem separately, something like that. Yeah, you don't care about this. But yeah, just show you. Yeah, okay, so that's this is called Hall's theorem, where yeah, basically if all of the subset here there are enough neighbors, then you can actually find a perfect match. Okay, yeah, and this proof is yeah, because it's by induction, you can construct the solution as well. Of course, you can use soft card, but yeah, you can actually construct using this induction as well, because this will prune the size of the graph bit by bit, and you can build from 1, 2, 3, and something like that. Okay. Yeah. And then another sufficient condition for a graph to be to have perfect matching is that if they are regular, you know what's regular graph? Yeah, regular graph is, and this is not only for tripartite graph, but regular graph is a graph where the degree is the same for all nodes. Right? So if all the nodes have 2 degrees, it's called regular. Okay? And in a regular bipartite graph, of course, if the degree is greater than 0, it actually has a perfect matching. Yeah. So if all of the nodes, including the right side, including the right side. Otherwise, you can construct a graph that looks like this, right? Yeah. Even though they all have two degrees, there's no perfect matching. But if all of the nodes, left and right, have the same number of degrees, then they also have a perfect matching. Do you want to figure out why this is true?
Because of Hall's theorem.
Expand a bit more.
I don't remember exactly, but
Yeah, like if you have suppose X nodes on this side, then the corresponding nodes on the other side have to be at least the degree times X, but each node has degree, have most that degree. So if you have to cover at least X nodes on the other side.
Yeah, basically for each X here, for each subset of X, and this is subset here, not necessarily contiguous. Let's say this is X, and we know that, let's say the graph is K regular, okay, then, I so forgot precisely how this works, but yeah, I think it's quite like counter example, so, like, sorry, not counter example, contradiction. So, let's say there's actually less than nx nodes here, so let's say there's less than 2 nodes here, they're switchable, let's say all gathers to, no, sorry, let's use 3. So let's say they all gather like this, right? This is what is. Then there is a contradiction somewhere that one of the nodes has more than k between. Yeah. In order to, because this, the right side also has k, this, the incoming edge to the right has to be evenly distributed, and there is at least x nodes as well. Yeah, so that's why it satisfies the condition of the Hall theorem, therefore it means there's a perfect matching as well. Yeah. Okay. Yeah, something that you might have not known before, but yeah, it's yeah, as I mentioned earlier, it's probably not going to helpful for most tasks, but there is a small number of tasks that might be easier if you know this. But yeah, very rare, but still there is. Okay, and the last part, yeah, this is the last part before we go to lots of tasks. Is that there's a Dilworth's theorem. Again, some of you probably know, but yeah, basically in a directed acyclic graph, the minimum path cover is actually the maximum independent set. So yeah, the maximum independent set in this sense is the same as in the undirected graph, where basically you want to choose several nodes such that for each pair of nodes there is no edge in any direction from U to V or V to U, right? That's the maximum independent set in a directed graph. Yeah, and again, you can find minimum path cover using bipartite matching, so you can also find maximum independent set in a directed acyclic graph, right? Yeah, so again, sorry, yeah?
If you have a path of 4 nodes, then the maximum independent set is like 2 nodes, and the path cover is just 1.
Oh, sorry.
I think you need
the graph to be transitive. Yeah, sorry, yeah. Good point. So not only DAG, but yeah, because actually the formulation of Dilworth's theorem, if you read the Wikipedia, is on a partially ordered set, right? So it's a mathematical the terminology is that basically it's a set that some of the elements are comparable, like either A greater than B or B greater than A, but not necessarily all elements is comparable. And transitive property has to be satisfied in order for it to call partially ordered graph. A partially ordered set, sorry. So yeah, in this case, in the graph terminology, the DAG has to be transitive as well. So if there's an S from U to V, then there must be and V, there must be an S from U to W. Okay, I guess okay. Or in another way, the maximum independent set should be like for each node, for each pair of nodes U and V, there must not be a path from U to V or V to U. Yeah, that's another way of saying it. Yeah. Yeah. Okay. Yeah.
How do you construct that?
You read the proof of Dilworth's theorem. I forgot. Yeah. Let me see whether I can figure out quickly. Well, you can at least wait. Can you? Okay, if I remember correctly, the proof is constructive. So you can there's a one-to-one matching between. If this is the path, then this is the independent set. So you can construct. There's a one-to-one mapping, so you can construct it. But let me figure out how does that exactly work. I think it's like choose the. Might not be so trivial. I cannot forget. I'll take a look. Again, I also forgot, but it's not complicated. I remember that it's still feasible. Not like the four-color theorem. It's an impossible proof. Yeah. Or maybe any of you knows what this works and how to construct? Okay, I'll probably read the Wikipedia page later and come back to you. Of this theorem, yeah. Yeah?
One direction is pretty easy, like from the path. to the maximum independent set, you just choose the first node in each path.
Why is that why is that an independent set? Because like if this is the path, then if you choose these two, this is not independent set. Yeah.
I think the other direction is usually if you have an independent set, then no two of them can be in the same path.
Yes.
So they have to belong to different paths.
Yes, but there can be more paths, right?
Yeah, so that's one direction.
Okay, yeah. And then the other direction is so we know that the independent set. So we know that the number of paths is at least the independent set, right? And then
if you know that for every, imagine that two paths. If you know that for every vertex in the path, in the other path, if there is a path for another vertex in the upper path, so you can just merge the two paths. So at least two pairs or vertex in the two paths are not comparable. I don't know to explain the meaning.
so you're saying that if there are two paths, you can also say that there has to be two independent sets from this as well.
Yes.
Um,
I'm not pretty sure. I think that if you can compare every node in one path with every node with the other path, you can just merge the path. Not really sure.
how do you merge?
Huh?
How do you merge the paths?
Just taking the start and the finish because you know that are comparable.
Oh, okay. So you're saying the start and the okay, yeah. So the end of this and the start of this is yeah, but what if there are more paths? So yeah, basically, if there is k paths, we know that for any u and v member of the path, we know that the end of u is not comparable. There is no x from end of u to start of v, right? And the other way around as well. But why does that prove that there is exactly number of paths independent set?
I think I have.
Okay.
So you take the maximum independent set.
Okay.
Then every node is either less than some of those or more than some of those. Right? It cannot be incompatible.
Yes, because otherwise it's not maximum, right?
Yes.
Yeah. Okay.
You can split the graph into the ones that are less and the ones that are more. And split them into paths.
No, but a node might be more than some of the nodes and less than some of the nodes.
No.
No?
Because otherwise those would be comparable.
You're correct. Okay, and then?
You recursively color the path.
Okay.
And then you need to, like, the end of the path, you need to do a mapping with the independent set to extend the path to the independent set, right? So you have the graph, you have the nodes that are less than the independent set, the independent set, and the ones that are more.
Yes. So let's say this is the independent set. We put it here and then what do you do with this?
Path in this path and path in this path, and you need to join them through the independent set. The independent set is not in either path. So you do path in this path without connecting with the independent set, and path in this path.
Like you find a minimum path covering this?
Yes, and the same for this.
Okay.
And the number of paths is less than the independent set, right? Because the independent set in this path has to be less than the independent set in this whole graph, right?
Yeah, but then, so this is like...
to join the path
with the independent set.
So you're using like an induction, right?
Yes.
So you assume that on this graph, this theorem is true, yeah?
Yes.
Okay? So, because in this part, of course, the independent set is less than this, or at most this, the minimum part cover is also okay, and then?
And now you have to join the end of this path to the independent set. And you use Paul's theorem. If there were a set, to do the maximum, right? You need a maximum.
Mm-hmm.
So you use Paul's theorem. If there were a set here that has less, that has edges to less nodes here than this set, you could replace that into the independent set, and it would be more. It would have more elements. That makes sense. So if Paul's theorem does not hold, like if the condition for Paul's theorem does not hold, then that independent set is not maximum.
I see. Yeah, okay, So we know, so let's say there are 4 independent sets here. We know that there is less than 4 paths here, and then we try to match the paths. Okay, and it's either we can match or this is not maximum, right? Yeah, that makes sense. But it's a bit hard to construct later. Yeah.
I think I have an idea.
Uh-huh.
I think if you take the maximum independent set in the bipartite graph where we take the in node and the out node, like to solve minimum path cover, we create a bipartite graph where for each node we create an in and an out.
Yes.
I think if we take the maximum independent side of this graph, you check if both nodes are in the maximum independent side, I think you can just take them and it works.
So you take the maximum independent set
and then you say that it's the maximum independent set in the original graph if both the in and out nodes are in the maximum independent set.
Oh, so you also find maximum independent set on the bipartite graph?
Yeah, you find the maximum independent set in the bipartite graph.
Okay.
And you say that it's the maximum independent, that a node is a maximum independent set in the original graph if both endpoints in the bipartite graph are in the maximum independent set.
So in the bipartite graph, 2 nodes in and out, the in and out is in the maximum independent set if they are not in the minimum vertex cover, right?
Yeah.
Which means the path contains only himself.
Right.
Because in this construction, if we match a node, it means that they are part of a path that has longer than one node, right? So if you say that both nodes are not in the minimum vertex cover, it means that the path contains himself alone. And then you're saying they are.
Because if there's 2 nodes and there's a single path, it doesn't work, right? Yeah, I think it doesn't work. Fuck. Okay. I remember there was a construction that was something like this, but I don't remember exactly what the statement was. Okay, I'll think more.
Okay. Anyway. Okay. So after this, we'll just have some tasks. So I think what we do now is let's take some break. 30 minutes break. While we do that, some of us, if you want to read the Wikipedia page, I will also do that, and we'll see whether we can come up with a construction from the paths, because we already know how to get the paths from the bipartite matching, right? But now we want to convert the paths into the maximum independent set. So, yeah, try to figure out how that works. If I can, after the break, we'll discuss that. And I have some tasks as well. So yeah, let's do that. Let's take some break. 30 minutes. 30 minutes. Yeah. before we go to the task, let's talk about some of the constructions of the theorem that we talked about earlier, because it might be useful. Let's say conics theorem, if you can find a matching in a bipartite graph, but let's say the question is, how do you find a vertex cover? It's actually not that trivial. And actually, the proof for the construction for conics theorem will be used for the Dilworths as well, because we were going to use the maximum independent set of the bipartite graph to get the maximum independent set of the original graph, right? So yeah, for conics theorem, you can actually do something like this. So let's say, okay, yeah, we're going to use some examples to make it easier. So let's say, this is the bipartite graph. Okay. And the maximum matching here is 2, and this is a unique maximum matching. No, actually this also maximum matching, but yeah, not unique there. Okay, but anyway, so yeah, and how do we know that this is the matching, but how do we get the vertex cover from here? So the idea is we use the maximum, the minimum cut. So I hope you know there's also a theory called that maximum flow is equal to the minimum cut. So yeah, and how do we find a minimum cut? Is actually quite simple. We just so you know that, yeah, let's just think this problem as a max flow problem, where there is a X from source where the capacity is 1 there. Also there's a capacity 1 here, and in each of these edges it's infinite, the capacity. And we take a look at the residual graph. So after you run the max flow, we take a look at the graph, and the nodes that is reachable from S is in one of the cut, right? So yeah, basically it means that 5 is connected to S, and we know that S will not be able to reach T, because if it reaches, then there is more flow that we can go through, right? So we know that S and T is disconnected, and the node that is connected to S is in the S cut. So in this case, it's this. This one is not connected to S, because if you match this, then this S is actually going backward to S, right? This residual, there is no residual X on this anymore, right? And then this 3 as well, and this S is not matched, so this S is still going this direction. But since this S is matched, this S now goes to that direction, right? So actually 2 is also reachable from S, right? So but going this way, right? That's right? And 3 is also reachable from S, right? So this is the minimum cut. The square node is the one that is on the S cut, and the rest is on the T cut. And we can see here that the cut is 2, this edge and this edge, right? So ST cut is the number of edges that originates from a node in S cut to a node that is in T cut, right? Okay. So now that we know this is the cut, the minimum vertex cover is actually is this. So let's say this is the A node and this is the B node. So the node in A that is in the T cut, which in this case is this one, and the node in B that is in the S cut, in this case is this one. This is the vertex cover. Okay? And of course we can prove this, but the proof, if you only care about the construction, we don't need to prove. But basically, we can prove by contradiction that basically this is vertex cover, because if let's say there's an X that is not originates from this, let's say from here to here, then this one should belong to the S cut as well, right? Because there's an X from here to here. So this one should be in the S cut as well. And then we can also prove that the number of this, like the number of these nodes, is also equals to the number of matching. in this case equal to the number of cuts, right? Because the number of this is the number of cuts that we make here, and the number of this is the number of cuts that we make here. So it's equal to the number of cuts, and we know that the number of cuts equal to the number of max flow, or in this case the matching, right? So yeah, and just now we also get the vertex cover. So yeah, we prove Conics theorem from here, and then to go to the doers, yeah, it's actually quite simple, the construction. So the reason I choose this graph is because there is a path graph that corresponds to this, which is this, right? So this is the DAG, and if you use the previous tripartite graph construction to get the minimum path cover, we will get that graph. And the construction here is that if we choose the maximum independent set is the node X such that both AX and BX is not in vertex cover. So yeah, so in this case, because this is the vertex cover, right? This one and this one is the vertex cover. 2, 4, and 5 is maximum independent set on this graph, right? Which is true, right? 2, 4, and 5 you cannot compare any of the nodes. Yeah, so that's the construction. Yeah, and the proof here is that basically thanks to some people that helped me as well. So basically let's say n is the number of vertices in the original graph, m is the number of matching. Basically we know that the number of nodes that both the nodes is not in the vertex cover is at least n minus m. And it can be more than n minus m if somehow both of the same node is in vertex cover, right? M is the number of m is number of matching as well as number of vertex cover, right? Because it's the same. But we also can prove that it's also less than or equal n minus m by doing the previous one, where we say that if there are two nodes that is in the independent set, then they cannot be in the same path. Yeah, so that's why this is also bounded by n minus m, something like that. But again, if you forget the proof, don't worry, you still can construct. But what you must remember is that you take the node that neither AX and BX is in vertex cover. So that's the idea. Okay, let's talk about some tasks. We have only 15 minutes left, so let's see how many tasks we can go through. Okay, but any questions so far? Okay, so so this should be easy. Let's say you're given a grid n by n, some of the cells are holes, and we want a piece of wood of length n to cover these holes, right? And these holes must be covered, and each hole can only stretch length n, right? And it must be either horizontal or vertical, cannot be diagonal, right? So how do we solve this?
The words are width 1.
Yes.
Mínimo. Ask the question now. Wait.
Yes?
If there's a hole in line I and column J, you can join those lines. Like you build a bipartite graph, like lines and columns. And if there's a hole in line I, column J, you connect those two.
Okay.
And then you can run the max flow, and the answer will be the minimum cut, because you have the source connected to all the lines, and
and then on the columns, and then the sink, you connect the source with like capacity 1, and the sink capacity 1, and the lines in between capacity infinite. And then the answer is the min cut.
That's true, because once you construct the bipartite graph like that, the problem now becomes minimum vertex cover, right? Where, like, let's say there's a hole in row I column J, then either Ri or Cj must be chosen. Like, we can, like, putting a dot on J column is represented by taking Cj in a vertex cover, right? And if there's a hole here, then we either have to put a board here or we have to put a board there. So it's the same representation as either Ri or Cj must be chosen. So yeah, it's the same thing. We want to find a minimum vertex cover on this bipartite graph, and it's the same as the max flow or the maximum bipartite matching by Koenig's theorem again. Right? Okay. Okay. Now, let's say we are given a complete directed graph now. There can be cycles. Be careful. There can be cycles. We want to find the minimum path cover. Number of minimum path cover.
Complete graph. Okay.
Directed complete means for each edge there's only one edge, not like two edge. Two edge easy, just one to edge. But for each pair of nodes there's only one edge.
Ok, você quer saber o número de ciclos hamiltonianos que tem na...
Sorry? Yeah, there can be cycles. Oh, the path have to be, one path cannot repeat a node. Yeah, it's the same problem as before. One path cannot repeat.
Okay, so it's always one, right? The minimum path cover.
Why?
Because there's always a Hamiltonian path in the directed complete graph.
Why?
Because it is known.
Why?
Like there's a construction for it, but it's...
How?
I think you always have, like, you either have a strongly connected component, and then it's easy, or you have, like, a node that reaches everybody, or a node that everybody reaches it, so you can just set it off and put it in.
A strongly connected component does not mean it's easy to create a path. This is a strongly connected component, but it's hard to...
No, but like a complete strongly connected component.
How do you create a path from that?
So like, can't you prove by induction?
Sorry?
Can't you prove by induction? Like you assume that for every directed what was the terminology? Like directed complete graph. Okay, so for every directed complete graph of size n, you can create a Hamiltonian path.
Let's say you can create a Hamiltonian path, and then how do you, like, let's say there's an n plus 1, how do you do that?
Oh, okay, so you have to prove that there's an edge to the first... Okay, that's...
Close?
Unknowing.
It's close. The
Okay.
is close.
Oh, okay, so we can say that we can choose any node that has out degree at least one to be the first in the path, right?
So you choose a node that has an odd degree, and then you construct the graph on the rest.
Yeah.
But then this odd degree might be in the middle of the path, right?
But like, okay.
Yeah.
Suppose you have the path.
Okay.
And you want to add an extra node.
Yes.
Then if the last node connects to this one,
Yes.
you have a path.
We are done.
Otherwise, if that node connects to the first
Yes.
node of the path, you have a path.
Okay.
Otherwise, then you necessarily have two consecutive nodes that connect like this.
Yes. So let's say we have a path. So if this goes to here, we are done, easy. So let's assume the worst case that it goes this direction. If this goes to this, we are also done. So let's assume the worst case, right? And because this goes to here, this goes to here, there must be somewhere in here where it looks something like this, right?
Oh yeah.
And then we can yeah. So yeah, correct. The answer is 1, but yeah, that's the construction, right? So yeah, easy. Yeah. Any question? Yeah, so that's the construction. Yeah, it's well known, and yeah, that's construction. Not a short question.
There is a construction to like construct a Hamiltonian cycle in every strongly connected component in the Hamiltonian path.
Any strongly connected component, or
yeah, any strongly connected component in a directed complete graph.
Okay.
And like I only remember how to do the construction using this, but like it's like really it's really complicated. So
okay, I actually never know this one. So you're saying if there's a big cycle, like if the SCC is the whole thing, there's
a Hamiltonian cycle.
Okay. Next is let's say we are given a bipartite graph. We want to know which edges are in all perfect matching. There can be more than one perfect matching, right? We want to find which edges are always in the perfect matching.
I don't know if it's a good idea, but maybe the ones that rate Paul's theorem, like if I can find a subset that has exactly the same size in and out, then I can't take any of those edges because I would remove the condition for Paul's theorem.
No, but we can like. Yeah, you still can remove this edge. So this set has the exact like 2 and 2, but you can actually remove this.
Oh,
but,
I have to check which ones actually reduce the size of one of them as well.
Yeah. Yeah. So how do you do that?
If I have the subset, I can just check if that's the only one entering that node or exiting that node. But I have to have the subset so that's not very efficient.
Yeah, but you still have like 2 to the power.
Yeah.
Way too much.
No.
I think I found a way, but I mean, it is a little cheating. I think I'm cheating a little bit. Like,
sorry?
I think I found a way, but I think I'm cheating. I'm cheating a little.
Chill?
Cheating.
Cheating.
Like
Cheating?
cheating.
Cheating, okay.
Okay, like, we can, basically we have a bunch of arrays and we are excluding one edge in each. So if we divide and conquer that, we could add each edge at most log n times. Like, imagine a segment from 1 to n.
So you're saying find the perfect matching first, right? No?
No, like,
okay.
I have a segment from 1 to n.
Okay.
And each one is one edge.
Okay. Okay. What are you numbering 1 to n here?
The edges in the graph.
Okay.
So basically, we split in the middle.
Okay.
And the position, let's say L to R, is basically I didn't include any edge in this position.
Okay.
So basically, let's say I go to the left, I include all the edges in the right.
Okay.
My bipartite match. And I go like splitting, like a sector, you know. So, but there are at most log n levels, so each edge will be added at most once.
But you need to check if there's a perfect match in O1.
Oh yeah, but can't you count like the number of edges you added and check if it matches the perfect match?
No, like you have to check for every set if the
Because
adjacent
like
is bigger or
for
equal.
each case I have like the perfect match for I have the graph mounted and I can count the number of edges I added in the path.
Yeah, I think your solution would be something like E times square root of E. Assume you have used Hopcroft card times E log E, I think.
Yeah, something like that.
We work faster than this.
Você não pode rodar o matching toda vez que você fizer o bagulho.
Funciona, mas
You can get rid of the log, but just delete an edge.
Yes, sure. Yes. Can we do even faster?
Nossa, cara, ele botou um log sem motivo, velho. Você só acionou um log na
Verdade! Verdade.
Tem 7 que esse cara olha, esse cara olha.
Não, mas não é log E.
Sorry? This is E square root of E times E. And this assumes we can do a matching in E square root of E using Hopcroft card. Yeah. Okay. Uh-huh.
No, you only will cut any candidate. No.
Yes. Okay.
After that, you can go erasing one and putting it in. I think that you're going to use one. Only step the algorithm. Because if the receiver network, with the internet, you can add one float to the start to one strength node, and from the other node to the stick to the end, and that will erase the edge, and you try to send one extra float, and if you can, that edge.
Porque você tá ligado que tipo, o barra 7 match não consegue
Right.
usar uma flow.
Increase the capacity of
Pega uma flow lá, então. Aí o que você faz? Você remove o flow que você pegou da aresta que você está querendo testar. E aí você
This one, right?
flow de novo.
Yeah.
Você só
Can
vai
we do
mudar
better?
uma iteração da flow. Like better than this looks pretty good.
we can remake it.
A gente quer saber se tem um caminho alternante. Como que a gente checa se tem um caminho alternante quando começa uma tarefa? Não, ele pensou, ele não pensou. Caminho alternante. A gente pega a aresta, a gente vê.
Yes.
You make the edges of the person matching one to another, and the edges that are not present in the matching from this side to the other.
Yes.
And you only care about even cycles.
Okay.
And to find even cycles, maybe you can do external connected component.
Yes. Yeah, that's the optimal that I know. So the plus becomes E, I think. Yeah, so basically once we find the perfect matching, we want to find for each edge, and we now talk about the residual graph. So if an edge is part of the matching, they become in the other direction. And if this edge is actually part of a cycle, it means it's not critical. Like if there is a cycle like this, then we can actually swap. So yeah, so this means this is the match one, but if there's a cycle, we can actually swap becomes like this, like we swap basically, like yeah, basically if there is a cycle, like you're talking even cycles, but all cycles have to be even in this graph now, yeah. So if there's this cycle, yeah, this means this, and then this is used, you can reverse now. Instead of this, we use this, and this. So yeah, we find strongly connected component.
Okay, so I think I have a way without strongly connected components.
You have a what?
A way to do it without strongly connected components. Okay. So we only have to check if there is a alternating path that starts at a matched edge, right?
Yes.
Okay. So we can just do a DFS starting at every node that is matched, and see if we can find an alternating path.
That's easy, right?
No, that's E plus V.
No.
Because like if we start at a node, we have to go to the node that is matched, and we try to find an alternating path. Oh no, that is E plus E times V, right?
That's E times V.
Okay,
yeah.
Sorry.
That's E times V, yeah.
Okay, sorry.
Yeah, so if you do strongly connected components, become this, and then you just check whether this node is, like for each node in the left, is part of a, like the strongly connected component has more than one element, it's part of a cycle. Yeah. Then it becomes E square root of V times E, plus E. Yeah.
Is that part of the components that is thinking?
I actually have several more tasks, but we're out of time. So again, I will bring this forward tomorrow. No, Friday, because tomorrow is sponsor stop. But let me go to this task that I actually didn't prepare instead, but I suddenly came up to my mind because it's interesting as well. So while we're talking about this, okay, so this directed complete graph thing. So if you have a directed complete graph, yeah, this is also usually called a tournament graph. Just FYI, right? Okay, so a tournament graph is a complete graph. It's a directed graph where each pair of nodes is there is an edge, right? So another question that I think about when talking about tournament graph is that how do you find a node that has no in degree in OM? So let's say, okay, the number of edges is large, like n square, but let's say it's an interactive problem, so you can query like, what is the direction of an edge from A to B? Okay, so you can call like that, right? Okay, and then it will give you whether it goes from A to B or B to A, right? And then we want to find a node that has no all degree in something better than n square.
Then no out degree?
No all degree.
Okay, so what we can do is like you query two nodes. Okay. If let's say that the edge goes from node A to node B, we know that A is not a consideration anymore, so we remove A. And then we query B and like C, and we remove whichever one has an odd degree.
Okay.
And in the end we will only have one candidate.
Yes.
Right? And then we just check if there's an edge between each and everyone.
Yes.
Okay.
You ruin the problem.
Yeah.
By solving it too fast. Yeah. Yeah. Okay. Yeah. Basically, yeah. That's the solution. Yeah. Basically, yeah. Instead of from A to B, like let's say A to B, A to C, like let's say A, B, C, and then it fails to D. Basically, you don't need to check D to B, D to C anymore because we know that this is no longer a candidate. So you just continue D, whether it's E, F, and then, but then, let's say D is the answer, the candidate that we got, we need to check everything, right? To all the remaining ones because there's actually, D might not be the answer as well, right? So we need like 2M queries. Yeah. Okay, any questions? No? Yeah?
In this algorithm, couldn't you fall into a cycle, or is it impossible?
Yeah, there can be cycles. So if there is a cycle, it's like, then the answer is no. So, yeah, there can be like -1, the answer.
But even if you fall into a cycle, you can still be left with...
No, you cannot fall into a cycle. Like, you query A and D, A and C and D, and let's say A and D, the edge goes from A to D. You query D to E, D to F, D to G. Yeah. So you just the thing that you query with the rest is always like linear, 1 to M. Yeah. Any question? Okay. Okay, yeah. Yeah, I think I have 2 tasks left actually, but yeah, they are more complicated than this, so it will probably take more time. So let's just save it for Friday. And yeah, so that's all for today. Oh yeah, today's contest, it won't be thematic. It will, I think that's the term, right? It will be from a full set of contests, so it will cover all, and that also includes like there will be very easy questions because like it's a question, so yeah, don't be offended by those easy questions, yeah. Because it's a full set. And one more thing actually, one of you just now during the break asked me to, if you already solved the task, you can view other people's submission. So I just enabled that. If you have problems with that for privacy reason, you don't want your code to be seen because of you type stupid stuff there or something. Just let me know. We can work it out. Yeah. But I just enabled that you can see other people's submission if you have already solved the task. So if you mind, let me know. Yeah. Yeah. So that should be all for today. Yeah. And yeah. Oops. I just showed you some problems that you have not discussed.
You are pushing.